Quality Control and Improvement, Module 5, Lecture 3, Control Charts for Variables. In this lecture, we will look at the process capability and how we can use this to compare how well our process is doing and improve our performance. The main objectives for Lecture 3 are the same as Lecture 1 and 2. Design variable control charts to analyze a business or manufacturing product. Analyze a variable control chart to detect when the process is in control. So far, we discussed ways of monitoring the production process to ensure that it is in a state of control and there are no assignable causes of variation. A critical aspect of statistical quality control is evaluating the ability of a production process to meet or exceed preset specifications. This is what's known as process capability. So first, it's important to understand what product specifications are. These are often called tolerances. These are preset ranges of acceptable quality characteristics, such as production dimensions. So for example, if we're manufacturing lumber and and our production process is producing 2x4s, we want to, there's certain tolerances on the width and the length and the thickness of a 2x4 when they're manufactured. If we're producing soft drink, there's a certain tolerance on the can dimensions, the liquid that goes inside the can. All of those have to fall within a tolerance level. And so that's what we're trying to determine in this process capability is how well is our process actually manufacturing our product to the specifications that are required. So let's look at 3 examples of process variation relative to design specifications for a soft drink company. Let's say that the specification for the acceptable volume of fluid is preset at 16 ounces plus or minus 0.2 ounce. So this means that we want our production process to produce soft drink that has a volume between 15.8 and 16.2 ounces. We'd like our product to be manufactured within that tolerance band. So here we'll look at 3 different cases. So let's look at part A first. So in part A, we notice that the top of the chart has the lower specification limit and the upper specification limit. Those are 15.8 and 16.2 ounces. That's where we'd like our product manufactured. The bottom chart shows a histogram of our actual production process. And you can see there's obviously natural variation that we talked about. Not every can is going to be exactly 16 ounces. Some are going to be a little bit less, some are going to be a little bit more. But in this particular process, part in A here, our histogram is, you can see it closely matches these preset specification widths. Almost all of the output falls within the specification range. So that's one example. Let's take a look at example B now. Now look at example B. Here we have we have the same lower specification limit and upper specification limits. We can see now our production process really falls outside of this. We can see now that a huge portion of this, in fact, let's just chop this off here, from about here to there. So all this part here and all this part on the left fall clearly outside of our specification width. So these products, there's a significant number of products that are going to be either have too much liquid in them or too little liquid. We would say that this process needs adjustment. Obviously, we're manufacturing way too many products that are outside of our specification. So finally, let's take a look at part C. Here in part C, we can clearly see that the histogram of our process falls completely within the specification limits. Here, so this chart is at plus 3 sigma and minus 3 sigma from our target, which is 16 ounces, and 99.74% of the product falls well within the specification limit. So obviously, part C here is what is better than any of these as far as a process capability analysis. This is why we rely on this process capability analysis just as much as we do control charts to tell us how well our product is performing to specification. How well can we manufacture the product within tolerances? So formally, how would we define process capability? It's designated by the symbol C sub P. It's computed as a ratio of the specification width to the width of the process variability. So in other words, it's the tolerance limits, the upper specification limit minus the lower specification limit, divided by 6 times the variance, 6 sigma. So how do we use this value? Well, a value of the process capability index of 1 means the process is minimally capable. Example of that would be A in the previous slides. Our process is meeting its desired effect, but just barely. So if something goes wrong, the operator has a bad day, the machine is off a little bit, it's very easy for, if you're at a CP value of 1, for this thing to slip and become less than 1. So we would consider this process as minimally capable. A value when the CP index is less than 1, it means that the process is not capable of producing specification and must be improved. This would be an example of slide B. A value of the process capability index of greater than 1 means that the process variability is tighter than specifications, and the process exceeds the minimum capability. This example of this would be slide C, where we're well within the specification limits. So if we have any drift at all, we can still meet our tolerances and stay within our production values. The process capability ratio, C sub P, may be interpreted another way by finding a term P, which is equal to 1 over C sub P times 100%. So this is simply the percentage of the specification band that the process uses up. So in the first case we looked at, where C sub P was equal to 1, P would be equal to 100%, and the process would take up 100% of the specification band. In part B, obviously P is going to be greater than 100%. So in that case, that tells us that the process uses up all of the specification limit and then some. So we're going to produce many more products in part B that are outside of our specification limits. And part C is obviously the best case because the value to P is going to be much less than 100%. So in this case, if let's say it's 50%, well, you know, our process only uses us 50% of our specification band. We have much more room for error here in part C. C sub P is very valuable in measuring process capability. However, it does have one flaw. It does not take into effect if the process is centered with respect to the specification. So let's compare two machines producing the exact same product. In the top one, we have set the lower specification limits and the upper specification limits. So in both cases, the lower specification limit is 38 units. So let's say we're producing, filling up Coke bottles, and so this is maybe 38 ounces is the lower specification limit, and the upper specification limit is 62. We would like all of our Coke bottles filled within the upper and lower specification limits. So in the first case, you know, we have a nice normal kind of distribution. The mean is centered exactly on the top of the histogram. The variance here is 2. So, you know, what that means is that, you know, we're going to produce some Coke bottles that fill a little bit less than 50. We're going to produce some that are filled a little bit more than 50. But this process is clearly is capable because it has a CP value of 2. So if you calculate this, you know, it's 62 minus 38 divided by 6 times sigma, so you get 2. The interesting case is if you compare machine 2, you get exactly the same process capability ratio value of 2. However, what's the difference? Look at machine 2 here. It's producing products within specification. However, the mean is shifted. The mean is shifted over, looks like about 50, between 50 and 56. So, you know, here in this case, you know, I think if we looked at both of these machines, we would say that we would actually prefer the top case. We'd want the actual, we want this process centered between the upper and lower specification limits. So that case, if there's some drift and a little bit of variability, We got much further to go before we're producing products that are outside of specification. On the bottom machine, if we drift a little bit to the right here, we're going to be outside the upper specification limit. So, we need a measure to figure out exactly, define and show that the top machine is actually a better kind of deal. We'd rather have all of our machines where the process is centered between the upper and lower specification limits. So in order to take this process centering into account, we define a new process capability ratio known as C sub PK. Now C sub PK, what it does is it simply takes the C sub P value and divides it in half. It computes a C sub P upper and a C sub P lower, and it takes the minimum of those two values. So let's look at a couple of cases to try to explain how this works. So in the first case, we have a process that's exactly centered. The peak of the histograms is right on top of the mean. So this mean is actually 62 minus 38 divided by 2. It's the mean of the upper and lower specification limits. So here, if we compute C sub P, we get a value of 2. 62 minus 38 divided by 6 times sigma, which will be exactly 2. And it turns out the C sub P sub K value is going to be 2 as well, because we take so we take the minimum of the left half or the right half, and they're exactly the same. So for example, if we do the upper specification limits minus the mean divided by 3 sigma, we get 62 minus 50, which is 12, divided by 3 times 2, which is 6. So we get a value here of 2. And it turns out that if you take the mean minus the lower specification, 50 minus 38, you get 12, divided by 3 times sigma. You also get 2. So these are both of these are has or 2. So, it doesn't matter which one you take. C sub PK is going to be equal to C sub P in that case. So this shows that if these are actually equal, the process is centered. And that's what we'd like. We'd like a process that's not only has a big C sub P value, but is also centered. So in that respect, C sub PK takes that centering into account. Now let's look at case B, where the mean is shifted to the right. In this case, the C sub P value is still going to be 2, because C sub P doesn't take that centering into account, but C sub PK is going to be much less than that. It's going to be 1.5. So if you continue this kind of thing on down, if you look at part E here, which is kind of a worst case scenario of these, C sub P value is still 2, but here C sub PK, if you calculate this, it's minus 0.5. And clearly, if you look at all these processes, we prefer process A here. We want not only do we want a big C sub P value, but we want the process centered. So in that respect, C sub PK is a better measure of process capability. In fact, some people would say that C sub P is a measure of potential capability, whereas C sub PK is a measure of actual capability. So let's work an example. Let's compare the C sub PK value and the C sub P value for the following machine, and let's interpret the findings. So the machine has an upper specification limit of 110 and a lower specification limit of 50. The process has a variance of 10, and the process mean is 60. So if you compute the C sub PK value from the data given, so again, you compare the lower specification to the upper specification. So 110 minus 60 over 3 times sigma is the first term, and then 50 minus 50 over 3 times 10. So here again, we're subtracting the lower specification limit minus the mean divided by 3 times sigma, the upper specification limit minus the mean divided by 3 times sigma. So you have to select the minimum between 1.67 and 0.33, which gets you 0.33. So the C sub PK value is 0.33, which means the process is not centered. However, if you compute the C sub P value, you get 60 over 6 times sigma, you get 1. So here's a case where the C sub pk value is 0.33, the C sub p value is 1. Uh, so, this process is clearly not centered, and so we would say this process is not capable.